Today, I'll be assessing the effectiveness of biomimicry materials in reducing the urban heat island effect in Phoenix, Arizona. So first, I'll be going over the context and urgency of this study. Right now, the world is urbanizing, and actually, 55% of the world's population live in cities right now, and that will increase to 68% by 2050, according to Ritchie and Hoser's 2018. Now, that will actually contribute to this phenomenon known as the urban heat island effect, where temperature is higher in urban areas compared to the rural areas, and it has many detrimental effects due to this increased heat stress that I'll go more in depth into in the literature. Now, I'll be going on an overview of the urban heat island effect and solutions to it. So once again, the urban heat island effect is when urban areas experience higher temperatures than their rural counterparts. And there's a myriad of variables that can contribute to it, but for this study, we will primarily focus on land cover and use, which was identified by Harmey and Choi 23. They say that because of random urban sprawl, that these impervious surfaces and land use, such as concrete, can actually hold heat during the day and then release at night, which can exacerbate the urban heat island effect intensively. Now, there's many impacts that they identified, such as it can contribute to climate change and worsen it, or it can have worse air pollution in the city, increase cooling energy consumption, and increase the water usage, and there can be more storm events. And this can have immense amount of health risk as well, as Renaud identified that it can cause more heat rash, heat cramps, heat stroke, and even death because of this increased heat stroke, or this increased heat stress, which brings me to why I believe this problem is very urgent, as I live in a city right now, and this increased urban heat island, or this increase in the even urban heat island effect can affect me. And one city in particular, in the city I live in, is Phoenix, Arizona. In fact, because of its increased urbanization, which has happened from according to the Harmey and Choi 23, say that Phoenix has been actually urbanizing by 21.58% from 2001 to 2014. And that's because agricultural lands are now being turned into urban and suburban developments. And also they say that this city is particularly good at identifying how the variables of the urban heat island effect because of its clear and constant optic weather, which means that it can actually exacerbate the urban heat island effect very much, and that there's less external factors that can actually contribute it and change the variables that contribute to it. Now, since this urban heat island effect can have so many negative impacts, there's a clear need for a solution. So one way researchers have tried to find a solution is through a biomimetic framework. Biomimicry is modeling nature to create sustainable models, or to create sustainable designs. And there are multiple ways how people have tried to implement this method. One is by using biological organisms by copying their form or their process or an entire ecosystem and using them as a guiding mentor to actually creating engineering solutions. And the underlying warrant for why this is a good framework for engineering is because life creates conditions that are conducive to life. That means that if we want to find solutions to the urban heat island effect, we can use organisms that already use forms, processes, or ecosystems to actually deal with this problem. Now, two key studies that I'm going to identify right now that have used a biomimetic framework to deal with the urban heat island effect is Han et al. 2015 and Araki et al. 2021. In the Han et al. Study, they biomimicked a plant called the Galanthus nivalis, and because of its properties that are used to mitigate this micro greenhouse effect, and they found that using this biomimetic framework that it actually decreased the heat. And in the Araki study, they biomimicked the Saharan ants' reflective properties, and that was used to actually mitigate the urban heat island effect in their city of Casco and Tubo of Panama. However, from these two studies, there's a clear gap. One is that these reflective materials have not been used in climates like Phoenix with its hot and arid climate. And also, there's been no analysis of how these reflective materials effectiveness in suburban areas, since they were primarily used in urban areas. And also, these are just two studies of a multitude of studies that are trying to find solutions to the urban heat island effect, and there's not a lot of research on how we can actually use a biomimetic framework to find solutions to this, so which leads me to my research question of how effective are bio-inspired retroreflective surfaces when making suburban houses to mitigate the urban heat island phenomenon in Phoenix, Arizona? Which leads me to my methodology. For this study, I used an experimental design. The reason why I use an experimental design is because one, it is one of the most efficient ways to indicate that the effectiveness of reflectiveness is actually causing a decrease in heat. And also, it's been used in a multitude of other studies. For example, in the Han et al. Study and the Roque et al. Study. However, these studies differed in the ways how they actually created their experimental design. For this study, I chose to use the Roque study as my parent study because for 2 reasons. One is that the Han study only has another geometric aspect to its biomimicry, which means that there's another independent variable to the reflectiveness, which doesn't answer my research question effectively. And also, the software that they used was called Energy Plus, which focuses on energy consumption, which my study's not focusing on, which is mine is about heat mitigation. That's what the Iraqi study primarily focused on, is mitigating heat in its city. So by using the Iraqi study as my parent study, I used this software called env.met or -met, which is a computerized microclimate simulation software that consists of 4 software. One is DV Manager to actually create the material. Second is Spaces to create the simulation space. Third is ENVI Guide, which actually conducts the simulation. And fourth is Leonardo. So the process of actually doing this starts in DV Manager, where I created the material. To create the material, I based it off what a Roque did, which was the Saharan ant for its reflective properties. The values that were used was a 0.92 reflectiveness and a 0.9 emissivity to actually reflect what a Saharan ant, the Saharan ant's properties was. Then I went into Spaces and I created a test and base case off a neighborhood in Levine, Arizona called Vineyard Gardens to actually simulate the suburban area. And in the test case, the biomimic material was applied to all of the houses, and in the base case, there was no biomimic material. However, factors that stayed the same were like the greenery and also the surfaces on the ground. And third, I went into ENVI Guide and placed the test and base case into 4 simulations across in a 24-hour period across 4 seasons. I used September to represent fall, December to represent winter, April to represent spring, and July to represent summer. Then lastly, I outputted all of this data in the software called Leonardo, which leads me to my data analysis. In Leonardo, I outputted data for all the 4 seasons across over the 24 hours, and I collected data from specifically a coordinate 3622.3 for its good location in identifying how that reflectiveness actually mitigated heat in the area. And also because of my inability to check every point for the amount of time we have, since that'll be a lot. And the variables I chose to look at was first reflective shortwave radiation, because it allows me to see how many solar waves were actually reflected out into the environment. Second was the mean radiant temperature, and third is the potential air temperature, because this is what Roque used to see if heat was actually mitigated, and if the material was actually effective at mitigating that heat. And to see the difference between the test and base case, I chose to use an equation where I just had the test datum minus the base datum, and if there's a positive value, that means there was an increase in that variable. If there's a negative value, that means there's actually a decrease. And lastly, I use a Pearson's coefficient correlation to see if there's a correlation between the reflective shortwave radiation and the mean radiant temperature and potential air temperature. And the x value was the reflective shortwave radiation, and the y value was the mean radiant temperature and the potential air temperature. If it was closer to 1, that meant that if there was more reflective shortwave radiation, that means there was more mean radiant temperature and more potential air temperature, which leads to my results. So in this first graph, we're looking at the reflective shortwave radiation across a 24-hour period, specifically in April. So starting at 9 a.m., we can see that a gap between the test case and the base case starts to begin, which shows that the test case actually had a higher amount of reflected shortwave radiation. And this would peak at 2 p.m. and then start to decrease after that point until the gap would close, which when the gap would close, since the sun would not be out. So this shows that the reflected shortwave radiation increases when the sun is present. Now in the second graph, we're looking at the mean radiant temperature between the base case and the test case again in April. And we can see here that it starts to actually increase. It starts to increase and actually peak at 2 p.m. at 2.755 Celsius between the base and the test case. And that means despite the more reflected shortwave radiation, there's actually an increase in the mean radiant temperature. And then after 5 p.m., actually started to decrease and actually turned negative, meaning that it started to decrease the mean radiant temperature. In this third graph, we're looking at the potential air temperature. And it's almost identical to what happened in the mean radiant temperature, where there was first an increase and then it peaked around 2 p.m. and then started to decrease and actually turned negative around 8 p.m., which is probably because the sun was not out. And these results were pretty much seen across all of the other seasons and across all of the other seasons, and we can see this with this correlation value. So in September and April and July, all of them had R values that were actually around 9.0, which means that reflected shortwave radiation was highly correlated with both mean radiant temperature and potential air temperature. And the only outlier was December. However, this could be because there is less sun in this month. And also, we can see it's the same thing with the potential air temperature as well, with the mean radiant temperature. So this positive correlation shows that the more reflectiveness that we actually have could actually have a counterintuitive effect than actually reducing heat. And this is unlike my parent studies where they actually showed that it decreased heat, which I'll be going into more in the discussion. So for a summary of findings, the first finding is that there was a higher amount of reflected shortwave radiation in the test case compared to the base case. The second finding is that there was actually an increase of mean radiant temperature across all the seasons during peak sun hours. And the third was that there was actually an increase in potential air temperature across all seasons at peak sun hours. However, the fourth finding is that after sunset, both mean radiant temperature and potential air temperature actually dropped across all seasons, but it was still minimal at best. And also, the fifth finding was that there was a high correlation between reflected shortwave radiation and both mean radiant temperature and potential air temperature. Now, first, I'll be going over implications for the biomimetic framework. The first thing is that if there is a superficial analogy that we can make superficial analogies with biological organisms. So in this case, I use the Saharan ant for its heat mitigating properties. And we can see that we can actually reproduce these. We can reproduce the forms that we see in biological structures and in engineering. And the second one is that there can be a tangential analogy. So this study only uses Mentor for its heat mitigation, but this is not specific to the problem because there's still other variables that are related to the urban heat island effect. So this could have led to the result that was not expected, which was a higher mean radiant temperature and potential air temperature, despite there being more reflectiveness. And lastly is that we should probably make more hyperspecific and biological analogies when using biomimicry, which can actually have a more positive effect. We can see this with the Han study, where they used the Scalanthus nivalis because it experienced a similar effect that was similar to the urban heat island effect, and that actually led to a decrease in the urban heat island effect's impacts, compared to this study where it was not seen at all. Now, for implications for the material, is that we can see that there was that the retroreflective material was associated with a higher amount of reflected solar rays. But however, this reflectiveness was not effective at mitigating the urban heat island effect during peak hours. So this is not lined up with past research, such as the Iraqi evidence such as my parent study. However, it does align with the assumption that Han made during his study that higher albedo is not recommended for exterior walls because these solar rays can be reflected back into the surrounding environment. This aligns well with another study done by middle of 2020, where they used reflective properties on pavements and actually found that it led to an increase in mean radiant temperature. That's what happened in my same study because the solar waves were reflected back into the environment, which means that instead of it being held in at night, actually we just went back to like the surrounding environment. So that goes to my third point, is that since impervious materials can actually hold heat during the day, these reflective materials could potentially stop this effect from ever happening. As the material minimizes the amount of heat held in these house walls because it's reflected outwards and not held inwards, like we do with current housing. So for future research, this demonstrates that we need to acknowledge how we actually place these reflective materials, and that right now the best option probably is to do it for roofs because it only reflects it back into the air and not into the surrounding air and surrounding environment. And also, we need there's not a clear, explicit difference on how reflectiveness actually affects in different climates. And also, there just needs to be more research in other different types of climates, such as temperate and also colder areas. And lastly, for my limitations, One limitation is just the freeware limitations of the ENVI-MED software. Is that one, it was limited in a simulation size of 50 by 50 by 40. So that meant that I could not do a larger study of a larger suburban area. And also, this led to less detailed surfaces, which meant that there were only rectangular structures with flat sides, which may have led to an increase in reflected shortwave radiation because most of the surface was a reflective material, instead of adding such other surfaces such as windows, which could have changed how much solar waves are actually reflected. And also for the findings, this was not an average of all the potential air temperature and mean radiant temperature, since it was only on one coordinate, so that might not be the same for other coordinates in the simulation. And also it should only be applicable to studies where it actually uses the Saharan ant as a guiding mentor, and also it should only be applicable to desert climates and not to other climates. And lastly, it's only related to one neighborhood, so the findings of this study should not be applied to large-scale urban environments.